So this is an example problem that actually combines two of the things we're learning. One is translational equilibrium, and the other is the spring force. So, translational equilibrium. 25 kilogram mass hangs from a spring, stretching the spring from its equilibrium length to some other length. So translational equilibrium, that means the sum of forces in the x direction or the y direction, well actually both, are equal to 0. The x direction, it sounds like, isn't really involved in this problem. So I'm going to only look at translational equilibrium in the y direction. So the sum of forces in the y direction has to be equal to 0. So that's translational equilibrium. We're also going to be looking at Hooke's law. Fs is minus Kx. Okay? And these are both vectors. Okay, so knowns and unknowns. Known. N is 25 kilograms. Also, we're going to need gravity. G is 9.8 meters per second squared. We've got an equilibrium spring length. So L equilibrium is 0.2 meters. And then the length stretched, it says it's stretched to a length of 0.3 meters. So it starts out 0.2, you hang something on it, and it goes to 0.3. All right. Unknown, the thing we're looking for is K, spring constant, K. So we're going to need this, Fs equals minus Kx. Do we know either of these, F or X? The F. So if it's hanging there, the spring applies a force upward. There's something else that applies a force downward. So if I start out, my spring is here, 0.2 meters. Then I hang something on it. It's now 0.3 meters. With that mass of 25 kilograms. Okay? So that's what's happened. If I draw a free body diagram of this mass, mg down, and then there's a tension up. The spring has a tension in it, pulling it up. And that tension is the spring force. So the magnitude of the tension is Kx. The minus sign means the direction the spring stretched, it's the other way. Okay? Sum of forces in the y direction, now I've got it. If we call this the plus direction, upward, sum of forces in the y direction, that's this tension. So K times X. And there's also gravity, mg, that's in the downward direction, so that's a negative. So Kx minus mg has to be equal to 0. So that means K, which is what we're solving for, add mg to both sides, divide both sides by x, mg over x. Easy enough. So mg, that's 25 kilograms, 9.8 meters per second squared, over x. What is x? I have a 0.2 meters, I have a 0.3 meters. Now remember, x is the distance that it is stretched or compressed from the equilibrium position. So it's not 0.2, it's not 0.3. It's the difference between those two. That's what the x is. So with nothing hanging on it, it was here. You put something on it, stretched to there. It's that length that it's stretched. So this is 0.3 meters minus 0.2 meters. Now we can solve. K is 2,450. And what are my units on this? Now we can use dimensional analysis. So dimensional analysis, we can say kilograms times meters per second squared divided by meters. Meters cancel. This has to be kilograms per second squared. There's also another possible unit for it. Kilogram meters per second squared, that's newtons. And then on the bottom there were meters. Instead of calling it kilograms per second squared, we'll use newtons per meter. So that's the answer.